Hi, I'm Hololina. Welcome back to another one of my presentations. In this presentation we will be talking about the magnificent and mysterious outer space. Stay tuned. Outer space, or simply space, is the expanse that exists beyond the Earth and between celestial bodies. Outer space is not completely empty, it is a hard vacuum containing a low density of particles, predominantly a plasma of hydrogen and helium, as well as electromagnetic radiation, magnetic fields, neutrinos, dust, and cosmic rays. The baseline temperature of outer space, as set by the background radiation from the Big Bang, is 2.7 kelvins, 270.45 degrees Celsius, 454.81 degree Fahrenheit. The plasma between galaxies accounts for about half of the baryonic, ordinary, matter in the universe. It has a number density of less than 1 hydrogen atom per cubic meter and a temperature of millions of kelvins. Local concentrations of this plasma have condensed into stars and galaxies. Studies indicate that 90% of the mass in most galaxies is in an unknown form, called dark matter, which interacts with other matter through gravitational but not electromagnetic forces. Observations suggest that the majority of the mass energy in the observable universe is dark energy, a type of vacuum energy that is poorly understood. Intergalactic space takes up most of the volume of the universe, but even galaxies and star systems consist almost entirely of empty space. This treaty precludes any claims of national sovereignty and permits all states to freely explore outer space. Despite the drafting of UN resolutions for the peaceful uses of outer space, anti-satellite weapons have been tested in Earth orbit. Humans began the physical exploration of space during the 20th century with the advent of high-altitude balloon flights, followed by manned rocket launches. Earth orbit was first achieved by Yuri Gagarin of the Soviet Union in 1961, and unmanned spacecraft have since reached all of the known planets in the solar system. Due to the high cost of getting into space, manned spaceflight has been limited to low Earth orbit and the Moon. According to the Big Bang Theory, the very early universe was an extremely hot and dense state about 13.8 billion years ago, 34, which rapidly expanded. About 380,000 years later, the universe had cooled sufficiently to allow protons and electrons to combine and form hydrogen, the so-called recombination epoch. When this happened, matter and energy became decoupled, allowing photons to travel freely through the continually expanding space. 35 Matter that remained following the initial expansion has since undergone gravitational collapse to create stars, galaxies, and other astronomical objects, leaving behind a deep vacuum that forms what is now called outer space. As light has a finite velocity, this theory also constrains the size of the directly observable universe. This leaves open the question as to whether the universe is finite or infinite. The present-day shape of the universe has been determined from measurements of the cosmic microwave background using satellites like the Wilkinson Microwave Anisotropy Probe. These observations indicate that the spatial geometry of the observable universe is flat, meaning that photons on parallel paths at one point remain parallel as they travel through space to the limit of the observable universe, except for local gravity. The flat universe, combined with the measured mass density of the universe and the accelerating expansion of the universe, indicates that space has a non-zero vacuum energy, which is called dark energy. Estimates put the average energy density of the present-day universe at the equivalent of 5.9 protons per cubic meter, including dark energy, dark matter, and baryonic matter, ordinary matter composed of atoms. The atoms account for only 4.6% of the total energy density, or a density of 1 proton per 4 cubic meters. The density of the universe, however, is clearly not uniform. It ranges from relatively high density in galaxies, including very high density in structures within galaxies, such as planets, stars, and black holes, to conditions in vast voids that have much lower density, at least in terms of visible matter. Unlike matter and dark matter, dark energy seems not to be concentrated in galaxies. Although dark energy may account for a majority of the mass energy in the universe, dark energy's influence is 5 orders of magnitude smaller than the influence of gravity from matter and dark matter within the Milky Way. Outer space is the closest known approximation to a perfect vacuum. It has effectively no friction, allowing stars, planets, and moons to move freely along their ideal orbits, following the initial formation stage. However, even the deep vacuum of intergalactic space is not devoid of matter, as it contains a few hydrogen atoms per cubic meter. By comparison, the air humans breathe contains about 10 to the 25th power molecules per cubic meter. The low density of matter in outer space means that electromagnetic radiation can travel great distances without being scattered. The mean free path of a photon in intergalactic space is about 10 to the 23rd power km, or 10 billion light-years. In spite of this, extinction, which is the absorption and scattering of photons by dust and gas, is an important factor in galactic and intergalactic astronomy. Stars, planets, and moons retain their atmospheres by gravitational attraction. Atmospheres have no clearly delineated upper boundary. The density of atmospheric gas gradually decreases with distance from the object until it becomes indistinguishable from outer space. The Earth's atmospheric pressure drops to about 0.032 Pa at 100 kilometers, 62 miles, of altitude, compared to 100,000 Pa. Above this altitude, isotropic gas pressure rapidly becomes insignificant when compared to radiation pressure from the Sun and the dynamic pressure of the solar wind. The thermosphere in this range has large gradients of pressure, temperature, and composition, and varies greatly due to space weather. The temperature of outer space is measured in terms of the kinetic activity of the gas, as it is on Earth. However, the radiation of outer space has a different temperature than the kinetic temperature of the gas, meaning that the gas and radiation are not in thermodynamic equilibrium. All of the observable universe is filled with photons that were created during the Big Bang, which is known as the cosmic microwave background radiation, CMB. There is quite likely a correspondingly large number of neutrinos called the cosmic neutrino background. Magnetic fields have been detected in the space around just about every class of celestial object. Star formation in spiral galaxies can generate small-scale dynamos, creating turbulent magnetic field strengths of around 5-10 μg. The Davis-Greenstein effect causes elongated dust grains to align themselves with a galaxy's magnetic field, resulting in weak optical polarization. This has been used to show ordered magnetic fields exist in several nearby galaxies. Magnetohydrodynamic processes in active elliptical galaxies produce their characteristic jets and radio lobes. Non-thermal radio sources have been detected even among the most distant, high-Z sources, indicating the presence of magnetic fields. Space is a partial vacuum. Its different regions are defined by the various atmospheres and winds that dominate within them, and extend to the point at which those winds give way to those beyond. Geospace extends from Earth's atmosphere to the outer reaches of Earth's magnetic field, whereupon it gives way to the solar wind of interplanetary space. Interplanetary space extends to the heliopause, whereupon the solar wind gives way to the winds of the interstellar medium. Interstellar space then continues to the edges of the galaxy, where it fades into the intergalactic void. For the majority of human history, space was explored by observations made from the Earth's surface, initially with the unaided eye and then with the telescope. Prior to the advent of reliable rocket technology, the closest that humans had come to reaching outer space was through the use of balloon flights. In 1935, the U.S. Explorer 2 manned balloon flight reached an altitude of 22 kilometers, 14 miles. This was greatly exceeded in 1942 when the third launch of the German A4 rocket climbed to an altitude of about 80 kilometers, 50 miles. In 1957, the unmanned satellite Sputnik 1 was launched by a Russian R-7 rocket, achieving Earth orbit at an altitude of 215, 939 kilometers, 134, 583 miles. The first humans to escape low Earth orbit were Frank Borman, Jim Lovell, and William Anders in 1968 on board the U.S. Apollo 8, which achieved lunar orbit. After researching space and learning about all its different aspects, as I am familiar with, you see SOS is pretty outrageous and beyond. I am quite fascinated by Earthlings' technology and creations. In order to achieve space orbit, it must have been really fun for the travelers as it is for me. But our rockets and spaceships are much faster, much faster. We have created our rockets to move and glide through space. It is something we know that I'd be curious to see if you Earthlings could figure out. Haha, well, so long Earthlings. I hope this presentation was insightful for you and brought you much information. Please like and subscribe if you wish to see more videos. Follow me on Instagram for updates on my day-to-day life. Goodbye for now.